started on today's notes over proving triangles congruent. We used two postulates yesterday, the side-side-side congruence postulate and the side-angle-side congruence postulate to prove triangles congruent. Today, we're going to be looking at three additional, one's a postulate, the other two are theorems. Again, a postulate is accepted as true, and a theorem can be proven. And once it's proven, then you can use it in other proofs. So let's get started. I'm going to just talk about each one of these, and then we're going to look at some examples. So the first postulate states it is the angle-side-angle congruence postulate, and it states that if two angles, and the included side of one triangle are congruent to two angles and the included side of another triangle, then the triangles are congruent. So right here, I have two angles, this angle and this angle, and then these angles that I highlighted in orange, and then the included side. Okay, and I've got that definition down here. We'll just talk about it, but it's in between those two angles. If those pairs of angles and those sides, that pair of sides, are congruent, then I can conclude that the two triangles are congruent. So two angles and an included side, that is the angle-side-angle congruence postulate, or the angle-side-angle postulate, or ASA. Let's look at the next theorem. It is the angle-angle-side congruence theorem. It states if two angles and a non-included side of one triangle are congruent to two angles are congruent to the corresponding angles and non-included side of another triangle, then the triangles are congruent. So I have two angles and a non-included side. If you can prove that these pairs of angles and this pair of sides are congruent, then you can confirm these triangles are congruent. So that is the angle-angle-side theorem. And the last one deals with right triangles. It is the hypotenuse-leg congruence theorem, or HL. If the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of another right triangle, then the triangles are congruent. So we've got two right triangles here. All right, that's what we're dealing with. And then the hypotenuse of this triangle, which is directly across from the right angle, right? And I know they're the same length because the same number of tick marks, are congruent. And then I have a leg, which is one of these other sides that comes off that right angle, are also congruent. Then I can conclude that those triangles are congruent. So let's talk about what an included side is, because this angle-side-angle has an included side, and this angle-angle-side theorem has a non-included side. So an included side is the common side of two consecutive angles in a polygon. It's between the angles, so two consecutive angles, one right after another. In this triangle right here, what is the included side between angle J and angle K? It would be segment JK. That's the included side. So the non-included side is not between the angles. It's a side opposite the angles. So in this particular figure, if I have these two angles, a non-included side would be KL or JL, right? So angle, angle, side, or angle, angle, side. Let's move on and let's dive into some proofs. In examples 1 and 2, we're going to be using the angle-side-angle postulate to prove these triangles are congruent. So we are given, first, number 1, everything you're given in your figure, however it's marked up is what you're given, or you could also be given anything like written, like this is written. Okay, so we've got some information here. First, we're given that angle ABD is congruent to angle DBC. Those two angles are congruent. I've written that here as my number 1. So what am I going to write as my reason? Given. Okay, the next statement says that ADB is congruent to angle CDB. Well, that's actually also given. That's just given in my figure, right? By those squares that indicate that those are both right angles. So that's also given. All right. So I know I have two triangles that are right next to each other and they share a side. I can always, always, always use the reflexive property of congruence to show that segment BD is congruent to segment BD by the reflexive property of congruence. So now I have, and I know, here's what's interesting about this one. You see those right angles and you think, oh, hypotenuse leg. We actually do not have a hypotenuse and a leg to prove these triangles are congruent, but we do have an angle, a side, and an angle to show that they are congruent. So you can still use these other postulates and theorems to prove that right triangles are congruent, but the hypotenuse leg theorem deals only with right triangles. So I've then concluded that triangle DAB is congruent to triangle DCB by ASA, the angle side angle postulate. Okay, let's look at example number 2. Example number 2, I've got some stuff written down here. I've got it marked up over here. What do these little arrows indicate? They indicate parallel lines. Okay, so we're probably going to be looking at and using maybe some angles formed by parallel lines when they're cut by a transversal. So let's kind of look at this. I've got, and you know what? It's totally marked up wrong. I need actually another set of, and I'll add that here. I need another set of arrows right here because these are not all parallel, but these two are parallel and these two are parallel. So I'll add another set of arrows right there. Okay, so the first thing we're given is that segment EF, which is up here, is parallel to segment DG, and we're given segment ED is parallel to FG. And we're given that over here. So that's given. And I've got it all written right there as statement number 1. You could break it out, one in statement 1, another in statement 2, or you could do it like that. Okay, so now I have that angle EFD is congruent to angle GDF. And that is a result of this line being parallel to this line and this transversal cutting it, right? That's how those angles are formed. And those are alternate interior angles. And the alternate interior angles theorem tells me that those angles are congruent. Now, I've got the next one as the alternate interior angles is the reason because I can use, because these lines are parallel, and here's my transversal. Now I can conclude these angles are congruent by the alternate interior angles theorem. And that is angle GFD and angle EDF. Sometimes it helps to, when you're looking at the angles off to the side, like only draw this line right here, ED and FG, like over here, and then draw your transversal. Then look at like, what are your alternate interior angles, okay? All right, so moving on, because sometimes it's like, it gets a little tricky when you have like barriers or boundaries like this. So anyways, moving on, here we have two angles, and we do have two triangles that are what? They're sharing a side right here, right? They're adjacent. They're next to each other. So what can I always use? The reflexive property of congruence to show that segment DF is congruent to segment DF by the reflexive property of congruence. And we've now proven that these two triangles are congruent using the angle, side, angle postulate. So angle, side, angle, right? In that order. That's why it's written in that order. Angle, side, angle, angle, side, angle. Let's move on. In these two examples, we're going to be using the angle, angle, side theorem. So let's look at example number 3. In example number 3, we are given that segment PQ is parallel to segment ST. And we're also given that R is the midpoint of SQ. That's right here, segment SQ. So And that's all we're given. Remember, don't ever assume in geometry. You can only work with what you're given. Okay, PQ is parallel to ST. We're given that. All right, so these two lines are parallel, or segments are parallel. We can then, from that, here's our transversal, here's a transversal. We can then conclude that angle RPQ, or just angle P, is congruent to angle RTS, or just angle T, because they are alternate interior angles. So they are congruent because the lines are parallel, and the alternate interior angles theorem tells me they're congruent. Now we're also given something else. We're given that R is the midpoint of segment SQ. And the definition of midpoint tells us that these two segments are congruent. If R is the midpoint, then RQ is going to be congruent to RS, or segment RQ is congruent to segment RS. If I'm going too fast and you need to pause the video, rewind it, please do so. I'm just going to keep moving on. The next step says that PRQ is congruent to SRT. Okay, that's true. How is that true? What tells us that these two angles are congruent? The vertical angles theorem, right? Vertical angles are congruent. So that's all we've needed. We have an angle, and a side. Angle, angle, side. We can therefore conclude, because we've proven, right? We have our angle here. We have our side here. We have our angle here. All right. We've concluded all that, or proven all of that, and justified it. So we can conclude that triangle QPR is congruent to triangle STR by angle, angle, side. Okay, let's look at example number 4. Example number 4 says segment AB bisects angle DBC. Okay, that's this angle right here, DBC. Okay, DBC. And then it says that angle C is congruent to angle D. All right, so the first thing, we write what we're given, and it's already there for you. Segment AB bisects angle DBC. Well, the definition of angle bisector tells me that angle CBA is congruent to angle DBA. Those angles are congruent by the definition of an angle bisector, right? It splits it directly in half. All right, the next thing, we already have our reason to be given, so let's write our other given. Angle C is congruent to angle D, right there. Okay, so I have now two angles. What else can I do? What do you think you could put in your final two steps? I know that segment AB is congruent to segment AB by the reflexive property of congruence. I have now proven these two angles are congruent. These two angles are congruent. This side is congruent to itself, right? So I can now conclude that triangle ACB is congruent to triangle ADB by AAS, or angle, angle, side. Let's move on to our last two examples. We're going to use the hypotenuse leg theorem to prove triangles are congruent. And in both of these examples, you can see that we're dealing with right triangles. In number 5, it is stated that segment JM is congruent to segment KL. That's a given, okay? That's all we know, right? Except that they're right triangles. So segment JM is congruent to segment KL. I've already got it written there in statement number 1. The reason is it's a given. But guess what? Angle K and angle M are right angles. That's also given, right? That's given in our figure. It's not given over here, but it is stated in our figure by these little squares that indicate those are right angles. So now I'm dealing with right angles right here. I've shown this leg to be congruent to this leg. They are adjacent triangles, which means they share this side, which just happens to be the hypotenuse. By the reflexive property of congruence, segment JL is congruent to segment JL. Here's your hypotenuse, leg, hypotenuse, leg. So I can conclude that triangle JML is congruent to triangle LKJ by hypotenuse leg, or HL. Moving on, in our last example, we're given a couple things here, right? Okay, these two angles are right angles and they're congruent. These two sides are congruent, but we're also given over here that N is the midpoint of MO. Okay, so let's write our first given. N is the midpoint of MO. What can we then deduce if N is the midpoint of MO? What can we next conclude? That MN is congruent to ON, and that is by the definition of midpoint. The next statement says that MQ is congruent to PO. Well, what would that be? What would the reason be for that? It's another given. It was given in our figure right here, right? It can be given in our figure by the tick marks, or it can be given over here and not in the figure. Okay, so that's a given. We also know that angle PNO, that's right here, is congruent, and QNM are right angles. So these two angles are right angles. That's a given. Well, we stated that those are right angles, okay? And you could state that they're right triangles because of that, right? But we have shown that these two sides are congruent, and those are both legs of each right triangle. And these two sides are congruent, and each of those is the hypotenuse of that triangle. So we can then conclude, because we've shown a side and another side, the hypotenuse and a leg, and we've identified that it's a right angle or right triangles, we can then conclude that triangle MQN is congruent to triangle OPN by hypotenuse leg. And that concludes today's notes. This is day 2 notes over proving triangles congruent. I hope it was helpful.